Okay. Next up we have a fourth year student studying ethical hacking countermeasures at Abertay, Rorie Hood. Give the floor to Rorie.
Thanks, Adam. Okay, so far we've had two particularly interesting talks, or at least ones that I found particularly interesting. We had Alex's, which was on AV stuff, and then we had Nick's, which was on Android exploitation. And I find that particularly good because my talk kind of fits slam bang in the middle of both of those. What I want to talk to you today is about rootkits, and basically how they've migrated from the traditional desktop environment onto mobile platforms, and why this is going to be a big problem. So as Adam said, I'm a fourth year ethical hacking student here at the University of Abertay, and my interests include malware development and low-level exploitation. It's worth noting that just because I'm interested in malware development doesn't mean I'm interested in releasing malware, to be used maliciously. That's not what I'm all about. I'm all about research. So, to begin with, if you decide I want to write malware, you generally have a motive. The most common ones seem to be for fun and for profit, but you also get malware for things like politics. I don't know if you saw the recent scandal with the creator of McAfee, or McAfee, whatever you want to call it, where he basically got caught putting malware on computer systems and then giving them away to government officials. And he apparently uncovered a whole conspiracy in the whole upper echelon of some small country, which I can't remember the name of. So, you decided you're going to write your malware for whatever your reason is. And the question is, how are you going to do it? Well, if your motive is for profit, then you generally want to target the largest demographic. Now, historically, that has always been Windows systems. And by Windows systems, I really refer to anything with an NT kernel, so all the modern Windows distributions. Historically, Windows has always had the largest market share, and that's generally due to reasons such as their pairing with Intel right at the start, through to the fact that all businesses began to use them, so that when people bought a home computer, they were familiar with Windows, and then that's the operating system they went on to buy. And in 2012, there were around 35 million new malware samples for Windows, and that was roughly double what was discovered in 2010. So malware is an increasing problem. But the way things are going, I reckon that malware, the dominance of the Windows systems is going to slowly deteriorate, not always in terms of the number of Windows devices, but certainly in terms of the number of the percentage number of Windows devices. Because if you think mobiles are everywhere nowadays, and that's really a smartphone phenomenon is really only 5 years old. And since 2010, mobile devices, including tablets, have been dramatically outselling desktop PCs. So as the amount of computing devices increases, the percentage that Windows really has on the overall market is beginning to decrease, which really makes Android the kind of big new vector that's coming out, because Android, it's got 75% hold on the market. 108.1 million phones currently, roughly. And its next closest competitor, iOS, only has roughly 15% of that market. Now, if we think that Android is open source and therefore subject to development, it's not going to just run on phones, it's not just going to run on tablets. We're also going to see it on things like embedded devices. I wouldn't be surprised if it's on my fridge within the next 10 years. Things like that. Android has a lot of potential to basically expand beyond the current phone and tablet market. I think that's what's going to happen. So Android is going to be really big. As I said, smartphones have been outselling desktops since 2010. So, what is a rootkit? Well, if you basically break the word rootkit down, it's pretty simple. Root is Linux super user. Basically, it's the administrator equivalent for Windows. And a kit is basically just a collection of tools or scripts. So together, what it actually means is it's a piece of software that allows you to maintain root access after compromise. Really what rootkits are all about is hiding your malicious files on the system from both the user and from antivirus. So if you look at Wikipedia, it'll tell you there's 5 different types of rootkits. I've got 6. Application-based rootkits were really the original. They work by patching or replacing standard file system tools such as PS and LS, which is process list and then just the list tool, and basically filtering output so that if you have a malicious file called malicious-file.exe, for example, then you can basically filter the output out of the list that LS would give you as part of its tool. And then you start to get library level rootkits. Now, library files in Windows are .dlls. In Linux and other Unix distributions or Unix-like distributions, they're .so files, which is shared objects. Now, the way a shared object works is that there is one copy of it stored in memory, and that means that multiple applications that require to use that library can basically both reference the same code, and it means you don't have to load 2 instances of one library file. Now, the kind of problem with that is that it's in memory pretty much all the time, and what you can actually do is you can patch it at runtime, and you can alter things such as the RO data. Bear in mind that you do have root access because you're creating a rootkit, and that you can alter it so that when a library function gets called, instead of calling the library function, you have patched the address that the library function is meant to be at so that it can call your custom library instead. And generally what you would do is, in your custom library, you would implement the same functionality, but in effect you would extend it so that while it does what it's meant to do, it actually goes on to do something else. And we'll talk about managed code rootkits and kernel rootkits in a second. The other 2 are really cool. So on things like your BIOS chip and GPUs, you have memory. Now, you generally can't view that, but as far as I understand, if you can find an exploit so that you can view it, then you can write to it. If you can write to firmware, you can basically put your rootkit on the firmware, and that's really dangerous because generally, if you want to get rid of a rootkit, you reinstall the operating system. It's gone. But nobody ever reinstalls their firmware. It doesn't happen. So you can virtually permanently and indefinitely have a rootkit on the memory space on firmware for as long as you want. And I find that really cool. And the other one's really smart. It's virtualization rootkits. Basically what they allow you to do is virtualize the operating system. Now the way virtualization works, an operating system is not allowed to know it's being virtualized. So what you effectively have is a really thin hypervisor piece of malware that emulates the operating system. And to the user, they just see their traditional desktop operating system. It doesn't appear any different. But in effect, the malware can monitor all your hardware and system calls. And it's really dangerous because, again, it's outward for the operating system. And there's a really good example of that. It's called the Stone Bootkit. And it works on all NT kernel versions. And then you've obviously got a hybrid, which is just a combination depending on what you're trying to accomplish. So we can say that rootkits have standard functionality. You want to be able to hide your malware from the user. That's pretty straightforward. You want to be able to hide any file associated with it. You want to be able to hide it from antivirus, obviously. Antivirus is a bit more effective than the user at removing malware. You want to be able to provide a point of re-entry so that you don't have to rely on your previous exploit to get back in. For example, there's a Java vulnerability going about at the moment for desktops. Chances are that'll get patched reasonably soon. So you can't always rely on the same exploit to allow you to get back in. So basically what a rootkit does is it allows you a hidden point of access where you can get back into the system. And another thing is you want to be able to survive the reboot, because if you're executing any form of malicious code, you switch the computer off, switch the computer back on, generally it will not be running. So you want some form of way of starting up, maybe as a process daemon at the start, some form of surviving the reboot. And then you generally want to have some form of other survivability from the user trying to remove it. There's quite a quite a cool version of rootkits, or at least a technique called a self-healing rootkit, where you basically have free components that constantly monitor to see if the other two exist. If one of them gets deleted, they basically reinstall it automatically. So basically you have to remove all free components of the malware at the same time. Otherwise they just constantly reinstall themselves. So this is the type of rootkit that doesn't exist on Wikipedia. It's quite new, last kind of 2.5 years. And a managed code rootkit basically attacks managed code environments. What I mean by managed code environment: any language that has a runtime that handles things like memory management, type safing, things like that. Really, we're talking about things like Java and .NET, Python and Flash. And it's a user space rootkit. So that does mean that it is not as privileged as a kernel-based rootkit would be, and it is limited to code that gets run on top of the runtime. But can anybody think of an operating system where all the apps pretty much run on Java? Someone said it? Android. So Android has its own implementation of the Java virtual machine, and it's called Dalvik. It's an instruction-based virtual machine as opposed to the standard Java stack-based virtual machine, and it doesn't really follow a lot of the Java specifications. In effect, it has its own specification. Instead of using jar files for Java archives, which are effectively zips, it uses the DEX format. Now apparently, even unzipped, the DEX format is a couple of percentages smaller than the jar file. I wondered if that was a typo that I read online, and that when compressed, it's probably a couple of percentages smaller than the jar file. And I think that's to do with the way it handles strings within the jar object, well, rather within the DEX object. But I'm not 100% on that. So every Java virtual machine needs a runtime environment. And the runtime environment really contains a lot of the standard classes that Java relies on. 3 of the most useful ones are the security manager, which does exactly what you think it does. It manages the security and enforces policies on Java applications and makes sure they're not doing things they're not meant to be. You've got the class loader, which loads in the classes as they're needed. And you've got the bytecode verifier that basically verifies that the bytecode that you run, which is compiled Java, meets the specification. And the situation for Android, it's basically that it meets the specification for Dalvik as opposed to traditional Java, because the bytecode system for Dalvik is slightly different and it's more optimized as far as I'm aware. So one of the interesting things about Java runtime environments, in fact, about any runtime environment for any managed code language that I've ever come across, is that they actually have no idea what they're meant to look like. For example, the Java class loader doesn't know what the Java class loader looks like. Which means if you basically go in and edit the class file for the Java class loader, you can basically manipulate what it does. So the interesting part about this is that your high-level Java code that says one thing isn't necessarily what you get when you run it on top of the Java runtime environment. Now, that's quite interesting, considering for Android, everything runs on top of Java. So basically what you can do is you can manipulate components, especially for things like antivirus that they rely on heavily, and you can basically change the way they work. If you were listing, for example, all the files in a directory using Java, well, there's a Java class that lets you do that. If you manipulate basically the output and you filter out certain files, you can basically hide all your malicious application files from the antivirus or from any other application that wants to view it. And that's really powerful. And it is a really big problem for Android, but fortunately it doesn't affect compiled binaries. That is, anything that's written in C, maybe using the NDK that compiles to an executable, as opposed to an APK file. It can't hide from them, because effectively the Java runtime environment runs above the actual file system. So again, there's standard functionality that you'd want to achieve. You want to survive the reboot. That's not so difficult because a lot of the components that are built into Java have to run at startup. You can basically manipulate the runtime environment so that it automatically starts your APK as soon as the phone's rebooted. And even more useful than that is the fact that phones themselves aren't really designed to be turned off. My phone currently has an uptime of about 500 hours, quite a long time. I charge it every night. And we can pretty much assume quite reliably that people are not going to turn their phone off, maybe for a week at a time. So even if, for whatever reason, you can't survive the reboot, chances are you can be on the device for long enough to get whatever you need. So the good thing about managed code rootkits is that they're effective against all apps, and that as a result, providing you don't screw it up, antivirus isn't going to be able to detect it. As I said, it doesn't affect compiled binaries. It is user space, so there's not as much power behind it as a kernel-based rootkit, and you will break things if you screw them up. But in general, it is a really effective form of rootkit against Android in particular, and it is cross-platform in the fact that it does work on different Java runtime environments on different platforms. So, kernel-based rootkits are probably my favorite. In the 1990s, it was pretty popular to use library-based rootkits. And you know, antivirus companies roughly knew what they were looking for, and they could scan libraries, and that wasn't really so much of a problem. But then Greg Coghlan comes along in 1999, and he releases a kernel-based kernel mode driver, which is the Windows equivalent of a loadable kernel module. And then all of a sudden, people that are writing malware kind of go, we can put this in the kernel. And of course, one of the really cool things with the kernel is anything that's in it automatically has full permissions. It can do absolutely anything it wants. So the Linux kernel is known as monolithic. That means it's one giant piece of code. Now, the problem with that is if you want to change something or add in a driver, you basically have to recompile the whole kernel. And that's a bit of a bitch. So they came up with this quite smart idea, which was loadable kernel modules. And basically, that is a dynamic way to extend the functionality of the kernel. And it's basically designed for writing drivers for hardware. You know, you don't want to have to restart and recompile your kernel every time you get a new USB pen, for example. So loadable kernel modules effectively allow you to load in code into the kernel. Now, obviously, this requires you to have root access to begin with. And they don't work like standard C programs. Now, the whole kernel pretty much is written in C with some x86 for hardware interaction. So if you want to create a loadable kernel module, you have to make it. So that requires you to have a kernel version. Now, fortunately, on a Linux distribution, you have your kernel source as part of your distribution. So you just compile it against that, and it works. Now the problem is it is quite version dependent, which is why most people will recompile a kernel module every time they need it for a different system. So this part is kernel space. The memory diagram is actually upside down. I realize that, and the stack should actually grow up. But I find it slightly easier to visualize it this way. So kernel space is basically where the kernel and the kernel modules reside. Anything that gets executed in here runs with absolutely full permissions, and you can do absolutely anything you want. And it's roughly 1 gigabyte in size that's reserved for the kernel. It depends quite how big it is. So what the kernel basically does is it does the whole core OS part. It handles your process space allocation. It handles all your memory requirements. It does your power management. And it basically interacts with the hardware. And it also provides a lot of functionality that your applications use to do the things they want to do. On x86 hardware, the kernel runs with what's known as ring 0 permissions. the Intel x86 architecture has a 4-tiered permission system, permission 0 to 4, permission 0 to 3. It turns out pretty much every operating system will only ever use ring 0 and ring 3, which is full permissions and limited permissions. So you're going to write a kernel-based rootkit, and you're going to use a loadable kernel module to do it. So to start with, you're going to need root. That's pretty straightforward. This is after exploitation, so we can assume we've already got that. You're going to need your kernel module source. We'll assume you've Googled about enough on the internet to be able to do that. That's fine. You're going to need a kernel. We know we've got a standard Linux distribution, so we have that. It's not a problem. And then you need a make file. The make file basically tells your operating system where the kernel is located to compile against, and then where the source code is that you want to compile. And then you make it. And if everything goes well, which sometimes it doesn't, you'll get this lovely little file called kernelmodule.ko. So your shared objects in Linux are .so files. It's pretty self-explanatory. A kernel module is a kernel object. And then if you want to load it in, you can use the insmod command. If you want to remove it, rmmod. And if you want to basically view all the kernel modules currently running on your system, it's lsmod. So you can now run code in the kernel. But if we run the lsmod command, we can see the kernel module running. We don't want that. So the question is, how do we hide a kernel module? It's not quite the same as hiding an application. And I was actually quite surprised. So in Linux, pretty much everything, and I pretty much mean literally everything, is a file. So it turns out there's a file that stores a list of all the kernel modules that exist on the machine. So basically all you have to do is remove the entry from the list. And the operating system has no idea it actually exists. Pretty straightforward, right? Turns out it actually is. That command will basically delete your current module from the list. Now, you've got to be careful while doing this that you keep basically a copy of the memory address that your loadable kernel module actually exists actually exists at, so that when you actually come to remove it, you actually know the memory address to reinsert your kernel module back into the list, because otherwise your operating system is never going to be able to find it. So that's pretty easy. So what happens if you want to hide other files? Okay, so one of the most fundamental data structures in the kernel is called the syscall table, or system call table rather. And basically, system calls are functionality that the kernel can provide to applications. It's basically an array of addresses, and each address is the address of a different system call. Now, system calls have allocated numbers, so I can't remember what they are off the top of the head, but if we assume that system call 3 is the system call for write, then basically we know that index 3 is where it's at. So you basically call system call 3, which is the equivalent to write, if that makes sense. Now, it used to be that if you want to manipulate the system call table, you would basically just import it into your kernel module. And then the Linux developers kind of realized what people were doing with it, and they were like, that's probably not the best idea we've ever had. So as of 2.4 kernel, it's no longer exported. And I originally got to this, and I was like, oh, what do we do now? Well, it turns out you have to be able to find the syscall table address, because literally everything relies on it. So it turns out you can actually find it in system.map. Really basic command, basically just concatenate the file and then grep it for the syscall table. And that's the memory address that system call exists at. Now, you can either do this like I've done and then put it into your kernel module and say this is where the system call table is, or you can do it dynamically during compilation. Again, it's just a script that will do it. So before we can basically manipulate the system call table, we need to know if it's write protected. Again, this information has to be made available so it can be checked. So all you got to do is concatenate proc CPU info, and again, just grep it for WP, which is the write permission bit. And it's a Boolean, it's 1 or 0, yes or no. So as we can see, to begin with, it's enabled. But that's okay, because we run in the kernel. We can do literally anything we want. So we take the address of our system call table, and we use that to basically set the virtual page address to read-write, and that basically makes our system call table writable. Okay, we can now write to it. So then what you do is use a technique. It's either known as trampolining or runtime patching. I prefer the term runtime patching because it sounds more interesting. And basically what you do is you execute the functionality of the system call you're meant to. If you were to change the way the system call worked, chances are it would have really dire consequences. And the system calls get used all the time, so chances are you would see an effect immediately. So what you want to do is you want to still execute the same functionality. And the way you do it is you basically insert a jump to a different area of memory that you basically have control over. So you might replace 2 bytes to do it, for example. You jump out to your memory that you control, you execute the code that was meant to be there, that 2 bytes, and then you execute some of your own code. And again, you be careful to make sure you don't crash it, which is horrendous when you crash the kernel. I don't recommend it. And I mean, you can repeat this if you need to, but at the end of the day, the system call still executes the functionality it's meant to, but you can manipulate it to do things that you want it to. So basically, when you run the ls command is dependent on X amount of system calls. The ls command does not have a magical list of everything in your file system. When you type ls, it goes and works out exactly what's in your file system at that point. In order to do that, it kind of prods the kernel and says, can you go look this up for me? And usually the kernel goes, yeah, I can. So the kernel will return a list, basically to the ls command that the ls command then prints out to you. Just like before, you can go on and you can filter that list so that files that you don't want to be displayed don't have to be displayed, but at the same time, it's still executing what appears to be regular functionality. And because your kernel-based rootkit is based in the kernel, antivirus really cannot touch it. I've never seen antivirus that implements kernel modules in any way, shape, or form. In my opinion, it would be a really horrendous idea if they did, because it's complicated. It's complicated enough doing it for one system. Imagine trying to do it for 1 million and make it work on all of them. It's going to be quite difficult. Now, that kind of moves on to how this affects Android systems. And we know that Android has a Linux kernel. Right, that's quite cool. That was actually one of its biggest punted features when it came out. But the problem is, in the same way that Linux is Unix-like, I would say it's more accurate to say that Android is Linux-like. The problem with the Android kernel is that it's not quite Linux, and it doesn't work. Well, it does work in relatively the same way, which is one of the best things about it. But, for example, standard binaries, it doesn't come with copy command, which turns out is really annoying. And it also doesn't have grep by default, which does my head in. And also, a lot of the standard Linux libraries, it doesn't have, partly because a lot of them it doesn't need. And on an operating system where memory is limited, processing power is limited, you don't need all these extra overheads. I do understand that as a design choice. And a lot of the libraries they do have are non-standard, which means they're Android specific. So I have a Samsung Galaxy S3. Who else has one out of interest? Hands up. Okay, there's a few, not as many as I expected. So it's probably the most common Android phone at the moment, or at least as I see. One of the cool things about it is that it runs a Linux 3.0 kernel. Again, being Android, it is open source, and the kernel is freely available to download from the Samsung website. It's quite large and does take a while. So let's start by assuming we have a rooted or exploited S-free phone. For fun's sake, let's assume Nick has just rooted it using his phone-to-own NFC vulnerability. So how do we basically take the knowledge we have? Basically, as a security community, Linux has been around for a long time. People have grown up as it's developed, and as extra techniques come out to basically bypass security mechanisms, people know what they're doing. And the question is Android similar enough to Linux to be able to port that knowledge? So what do? Well, again, if we want to resolve the system call table, we can. It exists in /proc/klsims. Now, as I said, Android has no grep. So when you're playing about with it, that's really annoying. So basically, if you want to read what it is, you basically concatenate it, and you basically stick it somewhere writable, SD card. And once it's in the SD card, you can basically cat it. And okay, you need to do a little bit of manual trolling through it, but it is there. And once you've got it, you can basically do the same thing. It's also really important in Android to have the kernel version. You can generally get it if you go into your settings, but you can also get it by catting proc/version. So cross-compiling binaries for Android is easy, to be honest. It's not difficult. You need a tool chain. I think you need kernel source. No, in fact, I don't think you even need kernel source. And it's pretty straightforward. But cross-compiling an Android kernel module, it turns out, is like the biggest pain in the ass I have had this year. So first of all, you need your kernel source. Remember, we needed that before. But this time you have to make sure you get the right one for your device. It's not that easy to find, but it is there. And once you've got it, you're sorted. You also need a tool that will cross-compile your kernel module. I found this one from Code Sorcery. It's not brilliant, but it does work eventually. A lot of dependencies, I noticed. And once you've got that all done, once you can compile your kernel module for Android, you hit an extra little bug. It's not really a bug. When you compile, you get your kernel object, and your kernel object has a var magic string that basically says the version number. Now, I didn't notice this. Somebody else noticed this and then put a workaround. Your var magic string tends to be different from the var magic string that your Android kernel expects. But it turns out, if you go in with a hex editor and you change the var magic string, providing you've compiled it against the correct kernel, it doesn't actually care and it will run it anyway. So you can run kernel-based modules, and you can then do exactly what you would do on a Linux-based system, and you can manipulate the system call table. So the good thing about it is that you can run code in the Android kernel, and therefore you can have kernel-based rootkits. And you are effectively the god of all phones. I mean, let's face it. The bad points are, it's not straightforward, and it takes a lot of hours of Googling to be able to get a lot of things to work. Part of that is just the fact that it's not been around long enough. Give it a couple of years. The examples, the tutorials will all get better. The tools we use to do it will get better. And it will become just as easy to write kernel modules, and therefore kernel-based rootkits for Android, as it is for Linux. So, in conclusion, it's all going to become easy. But it's going to take a couple of years. The documentation for Android, while there is a lot of documentation for a lot of the high-level things like the APIs, a lot of the low-level stuff doesn't really exist at the moment. A lot of it will be community-based, I reckon. But again, it's going to take a couple of years. In answer to basically the question, Android is Linux-like enough for you to be able to port a lot of your Linux knowledge, which is really handy. Either based through running code in the kernel, or through a managed code rootkit that basically screws up and manipulates the runtime environment, antivirus is horrendous against Android, or rather on Android. And part of that is the fact that, as far as I'm aware, and I have looked into this and decompiled some antivirus before, antivirus, as far as I can tell, does no heuristic analysis at all. it's all string-based. And as a result, while it might be able to catch older pieces of malware, it's very ineffective at catching new pieces of malware. And the way Android's growing, this is going to be a huge problem. You know, I don't really want a rootkit on my fridge, unless I put it there, which I'm very tempted when that happens. And basically, to summarize, if you're a Fandroid, you're screwed. Oh, I have no questions slide, but is there any questions? Yep.
I was under the impression that the default Android kernel wasn't built with module support. Is it vendors that are turning that feature off? Or?
Yeah, as far as I'm aware.
How would you deal with a situation where you've got root access on a phone and you didn't have module support? Is there anything you could still do with kernel space?
You could recompile it. Don't recommend it. Your user might notice. I'm not sure.
Is there any runtime stuff you can do with ring 0 to patch things into it?
Not that I'm aware of, but I haven't really looked at that avenue. No, to be honest, I'm not sure. Possible, but I think you'd have to recompile the kernel, which we would get caught. Is there any other questions?
When you're saying it's version dependent,
Mm-hmm.
how often do vendors change that? Is that kind of a really frequent thing, or is it only like major releases that they tend to?
I think it's major releases. The last couple of years, I've noticed between Android, because you know how you get a new Android phone every maybe 2 years, or you get a new phone in general. I've noticed that the version numbers seem to change significantly between them. I think the last kernel I was running on was a 2.4 kernel before my S3, and now the S3 is on 3.0. I think they try to keep up quite well with the current developments in the Linux kernel. Obviously, you know, as the Linux kernel gets better, you know, you want to incorporate as much of that functionality as you can. But I think it's really dependent on the developers and what they're thinking at the time and what kind of functionality they need. But it does seem to be quite version dependent. Anything else?
You know how you said that like, the Android is quite similar to Linux?
Yeah.
Like, you know, you said that you could do that command and it would remove the kernel module from the list.
Mm-hmm.
Could you do that on Android?
Yes, yes,
Yeah.
you can.
Well, if you're doing that, surely that means that the kernel module is loaded in memory somewhere. So
Mm-hmm.
I know it's a bit different, but with virtualization, you can take a snap like a memory dump.
Mm-hmm.
You'd then be able to quite easily search the memory dump for like the signature of the kernel module. Could you not do a similar sort of thing?
I don't see any reason why you couldn't. The advantage of removing the kernel module from the list is that the operating system has no record of where it currently is. As far as it's aware, it doesn't exist. That doesn't mean it's not in memory. I think you'd have a hard time searching for a memory trying to find it, but I don't see any reason you couldn't. But the problem is, like, antivirus, you know, a forensic analysis might do that.
Yeah.
Antivirus isn't going to do that. If antivirus starts doing that stuff, you know, the whole game changes.
Yeah.
But currently, that's not the way it
We need to
works.
start doing that.
Okay, thank you very much.